We are diving straight into Harness-1, reinforcement learning for search agents with state-externalizing harnesses. If you are building agentic loops right now, you've probably hit a wall where your agent just starts looping the exact same search query over and over. Or it completely forgets a crucial piece of evidence it found 20 steps ago.
Oh, yeah, that happens all the time.
Right. And this paper diagnoses exactly why that happens. We are forcing LLMs to do semantic reasoning and mundane bookkeeping simultaneously, all inside a single, ever-growing, append-only transcript. Their solution is Harness-1, which is an open-weight 20 billion parameter search agent. And it's trained via reinforcement learning to operate inside what they call a stateful search harness.
Which is such a brilliant way to frame it.
It really is.
Yeah.
And the results are just staggering. By offloading memory, deduplication, and evidence tracking to the environment, this 20B model hits a 0.730 average curated recall across 8 highly complex benchmarks. I mean, it completely obliterates the next best open model Tangi Deep Research 30B by 11.4 points. It genuinely goes toe-to-toe with frontier models like GPT 5.4 and Claude 3.5 Sonnet.
And, if you work in RL, the reason this matters isn't just the benchmark score. It's really the optimization bottleneck.
Yeah.
Because when you force an agent to optimize over a raw text dump, you just get terrible reward conditioning. By training the policy over an explicit search state rather than a flat transcript, the authors actually fixed the credit assignment problem. And that's the problem that has been, honestly, ruining agentic search for years.
Spot on. You're watching AI Paperslap, by the way, our YouTube series, where we summarize the absolute bleeding edge of machine learning research for you. So, okay, let's unpack this core problem with the standard React paradigm. I mean, reasoning and acting has been the default architecture for a while now, right?
Right, yeah. React is everywhere.
But when you apply it to long horizon search, it just seems to crumble under its own weight.
It absolutely crumbles. And it's mostly because of how current agents handle tool orchestration. Like, you give an LLM a search tool, it issues a query, and the results are just appended to the context window.
Just dumped right in there.
Exactly. Then it issues another query, and more text is appended. So as that transcript grows into, tens of thousands of tokens, the policy has to continuously reconstruct the useful state of the search from this massive, unstructured pile of raw observations.
It's like asking a researcher to write a comprehensive literature review on a giant whiteboard, but the rules are completely sadistic.
Oh, I love that analogy.
Like, they can only write at the very bottom of the board, they are never allowed to erase a mistake, and they can't use sticky notes to group related concepts.
Right, yeah.
Eventually, the whiteboard is just a noisy mess of dead ends and half-thoughts.
It's even worse than that, really.
Yeah.
It's a whiteboard where the ink is slowly fading at the top as they write at the bottom.
Oh, wow, yeah, the context decay.
Exactly. Because of context window decay and attention dilution, the LLM physically loses a strong signal on its earliest discoveries.
But I have to play devil's advocate here for a second, just looking at where the industry is heading. We have models pushing 1 million, even 2 million token contexts now. Doesn't infinite context just brute force this problem away? Like, if the model can see everything, why does the structure even matter?
That's the common assumption. But scaling the context window doesn't actually solve the optimization problem.
Really?
Yeah, because seeing a million tokens is not the same as acting intelligently upon them. The policy is still wasting a massive amount of its compute budget on mechanical bookkeeping instead of, actual semantic decision-making.
Oh, I see.
And when you are training via reinforcement learning, this creates a major credit assignment issue. So let's say your agent runs a really hard query that returns an empty set of documents.
Right.
In a flat transcript, the RL rollouts get nearly identical empty set rewards. The signal is totally flat.
Or, if the agent has a larger tool vocabulary, the cross-document structure becomes totally diffuse. I've actually seen this in my own testing. The agent often collapses into just repeating the exact same search calls over and over.
Yeah.
Because it's literally lost track of what it already explored 50 turns ago.
That is the classic failure mode right there.
Yeah.
And worst of all, when an agent ultimately fails to return the right final answer, the RL reward signal cannot easily tell what went wrong.
Right, it's too noisy.
Exactly.
Oh.
Was it a bad search query initially? Did it find the right evidence but forget it because it was buried 40 turns ago? Did it just fail to verify the claim at the very end? The reward signal is completely diluted by the unstructured mess of the transcript. So the model is penalized, but it has no idea which specific action caused the failure.
So if the transcript is the enemy of optimization, how do we physically replace it? I guess this brings us to the architecture of stateful cognitive offloading.
Yeah, the exoskeleton.
Right. Instead of a flat transcript, Harness-1 uses a two-tier working memory. And to be clear to everyone listening, this isn't just a UI wrapper for the user. This is the actual mathematical state representation the agent operates over. Let's break down the mechanics of that, starting with the candidate pool and compression.
So the environment takes on the heavy lifting before the LLM even sees the text. When the agent searches, the harness doesn't just dump the raw HTML or text back into the context.
Thank God.
Yeah, it handles BM25 sentence selection first. It ranks the text based on term frequency and inverse document frequency, keeping only the top, most relevant sentences per chunk based on that specific query.
They also run a really strict two-level deduplication process, right? They filter by chunk ID, which makes total sense, but then they use min-hash LSH content fingerprinting.
Yeah, that part is crucial.
I get BM25 for keyword relevance, but why min-hash? Like, why not just use a standard exact match filter or, I don't know, a cosine similarity embedding?
Well, exact match is way too brittle for web text. A single changed comma or an extra space completely breaks the match.
Oh, true.
And on the other hand, embedding models add way too much inference latency for a tight RL loop. You can't wait for embeddings every single step. Min-hash LSH, which is locality-sensitive hashing, is brilliant here because it mathematically hashes the content so that documents with similar engrams actually collide in the hash space.
Wait, so it groups them together mathematically?
Exactly. It lets the harness quietly delete redundant fluff. Think of like repeated press releases or boilerplate website navigation text. The harness strips it out before the LLM even spends a single token reading it.
And the beauty of that is that it still gives the RL algorithm credit for finding the document, right? The reward function sees the success of the search query without paying the massive token cost of putting duplicate text in the prompt.
Exactly. It's highly efficient.
Okay, so next is the curated set and the importance tags. The final output set is capped at 30 documents, but the harness does this fascinating thing called auto-seeding. On the very first successful search, the harness automatically seeds the top 8 retrieved documents straight into the curated set. Why do that? Like, why not make the model earn every single document it curates?
It's purely about RL training stability. If every rollout started with an empty curated set, the agent's early exploratory actions would almost never result in a complete, verifiable answer.
So it would never learn anything.
Right. The early RL rewards would be totally flat and indistinguishable. So by warm starting the state with auto-seeding, the agent's job gracefully shifts from building from scratch to refining an existing pile.
It gives it a foothold. That makes sense. Then the policy uses a specific curate tool to add, remove, and tag documents with 4 strict importance levels, very high, fair, or low. And when that 30 document cap is hit, the harness automatically evicts the lowest importance documents first.
The agent doesn't even have to manage the memory array itself. It just assigns the value. And then we get to the evidence graph, which is, in my opinion, arguably the most powerful mechanism in the entire exoskeleton.
The evidence graph is brilliant. So the harness runs a lightweight regex pass over every single incoming chunk to extract entities, specifically proper nouns and 4-digit years.
Just simple regex, yeah.
Right, but then it dynamically renders a compact map directly in the state, showing what they call bridge documents.
Bridge documents being those chunks of text that contain multiple frequent entities. This naturally connects separate pieces of evidence without the LLM having to read 50 paragraphs just to realize, oh, 2 documents, both mention the same 1998 antitrust lawsuit.
The environment literally draws a line between them for the model.
Exactly. It also highlights singletons, which are entities that only appear once.
And singletons are the perfect leads for follow-up searches on multi-hop questions, aren't they?
Oh, absolutely.
Because the agent doesn't have to reread the transcript to figure out how entity A relates to entity B. The harness just maintains the graph. Finally, there is the verification cache. The agent has a verify tool where it can write a specific claim and check it against the stored documents.
Right, and the harness runs the check and logs a definitive yes or no judgment, complete with a rationale, directly into the state.
Which acts as a massive dampener on hallucination. I mean, the LLM retains all the actual semantic power. It decides what to search, how to tag things, and when to stop. But the environment is the exoskeleton doing all the clerical work. It provides a stable, structured interface.
That's exactly it.
Okay, so you have built this beautiful, highly structured cockpit with buttons for curating, tagging, and verifying. But an LLM is, at its core, a next token predictor. It naturally just wants to yap.
It really does.
How do you physically force a 20B model to stop generating streams of text and start pressing these specific interface buttons? That brings us to the training recipe.
Yeah, you really have to train the rhythm of the operations. The researchers started with supervised fine-tuning, or SFT, but the scope was deliberately very, very narrow. They only used about 900 filter trajectories generated by a GPT 5.4 teacher agent.
I read that and had to do a double take. 900 trajectories.
It's just 900.
In the LLM space, 900 rows of data is nothing. Usually you need tens of thousands of examples to instill a complex new behavior into a model. How on earth did they get away with such a tiny data set?
Because the SFT phase wasn't about teaching the model facts or domain knowledge. It was purely about behavioral cloning for the interface mechanics.
Oh, I get it.
The GPT 5.4 teacher agent was just demonstrating the discipline of the exoskeleton, search, then curate, then verify. It teaches the model the norm of verifying a claim before it is allowed to promote a document to very high importance. 900 high-quality examples is totally enough to teach that muscle memory of the state interface.
So once it has the muscle memory down, they move to the reinforcement learning stage to actually make it smart. They used on-policy CISPO and trained it entirely on SEC training queries. Just 3,453 queries total.
Yeah, very targeted.
They ran a batch size of 128 with 8 rollouts per query. But I really want to dig into the RL dynamics here, specifically what the authors call the diversity-preserving incentive.
Oh, this is where reinforcement learning gets incredibly tricky. When they first ran the RL phase, without a specific reward for using a diverse set of tools, the agent completely collapsed. It found an exploit in the action space.
Let me guess. It just spammed the easiest tool that returned the most text.
Exactly. It spammed the fan-out search tool continuously. It would find a mountain of documents, completely bypass the curation and verification steps, and just try to guess the final answer from the noise.
Classic LLM behavior.
Right. Its recall just flatlined at about 0.53.
Because RL will always find the path of least resistance. If you only reward the agent for finding the final answer at the end of the episode, it won't do the hard, token-heavy work of bookkeeping. Generating a search query is cheap. Generating a complex verification rationale is expensive and risky.
That is the core issue, yes. So the researchers introduced a diversity reward that physically penalized the agent if it didn't use a balanced mix of its available tools.
Wow, okay.
It forced the model to engage with the state editing features. It had to search, read, tag, and verify in proportion. And once they added that diversity incentive, the agent was forced to utilize the exoskeleton properly, and the recall jumped to 0.60 during training.
That is wild. And this brings us to the transfer phenomenon, which honestly breaks a few unwritten rules of machine learning.
Yeah.
The RL training was exclusively on financial SEC queries, right?
Yep.
And the SFT data was mostly SEC, patents, and some web tasks. So what happens when you take this agent and test it on completely unseen domains, like complex, long-context QA or multi-hop reasoning data sets?
The results are what elevate this paper from a neat trick to a major breakthrough, honestly. Let's look at the source family benchmarks first, the financial and patent domains it saw in training. On those, Harness-1 showed a 7.9-point recall gain over the closest open baseline, which was Context-1.
Okay, that's a solid expected improvement.
But then you look at the held-out transfer benchmarks, data sets it had never seen, like long seal QA, seal QA frames, and hotpot QA. On those completely unseen tasks, Harness-1 showed a massive 17.0 point gain.
Wait, really? 17 points?
Yeah, that is a 2.2x larger gap on unseen tasks compared to the tasks it was actually trained on.
But a model is fundamentally supposed to perform best on the distribution it was optimized for. This is completely counterintuitive.
It is counterintuitive, right? Until you look at what the SFT and RL phases were actually doing to the model weights. The policy was not memorizing SEC tax codes or patent law in its parameters. It was learning domain general operations.
It was learning how to drive the exoskeleton.
Precisely. It learned how to look at an auto-seeded set and refine it. It learned how to read an evidence graph, spot a singleton entity, and execute a follow-up search to bridge a knowledge gap. It learned to backtrack when a verification check failed. Those specific cognitive operations transfer perfectly to any domain, whether you were looking for an obscure tax law loophole or answering a multi-hop trivia question about a movie director. The subject matter changes, but the mechanics of good research do not.
But researchers are naturally skeptical. I mean, how do we know the harness is actually doing the heavy lifting? How do we know the authors didn't just, accidentally train a secretly brilliant 20B reasoning model during the RL phase.
Good question.
To prove this, they ran inference time ablations. They systematically broke different parts of the harness at test time just to see what the model would do.
And this is where the behavioral signature of the agent becomes completely visible. For example, they disabled the importance tags. They just made the curate tool binary keep or discard. Instantly, the model lost its confidence signal.
It lost its memory, basically.
Yeah, the number of times it used the redocument and verify tools just plummeted, and it reverted to a wide, shallow, search-dominated loop.
It lost the ability to prioritize, so it panicked and just started Googling everything.
Exactly. Then they hid the evidence graph. The model still searched, but it completely failed to connect the dots on multi-hop queries because it couldn't see those bridge documents mapped out. And when they disabled all the harness mechanisms completely, the final answer recall dropped by 6.4%.
What's fascinating to me is that losing a state mechanism doesn't just mean the model has less information in its prompt. It physically changes the trained policy's behavior.
Yeah.
When you take away the editable state, the policy cannot execute the operational rhythm it learned. It's a fundamental regression in capability.
It proves that we have been looking at the bottleneck in agentic AI from the completely wrong angle. We've been throwing massive amounts of compute at larger context windows and larger parameter counts, hoping that if a model is just, smarter, it will naturally get better at long horizon tasks.
Right, the brute force approach.
Exactly. But Harness-1 proves that offloading state management into the environment is a vastly more efficient way to achieve frontier-level performance.
Which means the paradigm is fundamentally shifting for you, the engineers and researchers listening right now. We are moving away from basic tool orchestration, which is really just handing a massive LLM a calculator and crossing your fingers that it uses it correctly, to stateful harnessing.
Yes, giving the model a workspace.
Exactly. Giving the model a persistent, editable environment that handles the cognitive load of bookkeeping so the LLM can dedicate 100% of its compute to semantic reasoning.
It is a shift from optimizing the brain to optimizing the workspace the brain operates in.
Which leaves you with this final thought to chew on. If we can make a 20 billion parameter open model rival a massive frontier model simply by offloading its state management into the environment, what happens when we apply these state-externalizing harnesses to multi-agent systems?
Oh, that's a huge question.
Right. Imagine if each specialized agent in a swarm had an editable state environment tailored to its specific modality. A persistent visual state board for a vision model, tracking spatial relationships and objects over time outside of its context window. Or an execution state board for a coding model, tracking variable states and call stacks dynamically.
It would be incredible.
If we can build custom cognitive exoskeletons for every type of model, are we realizing that parameter scaling isn't the only path to AGI? Is harness engineering the true next frontier? Something to think about as you design your next agentic loop. Subscribe to AI Paperslop to stay updated on the absolute bleeding edge of machine learning research, and we'll see you next time.